Hi everyone! In this video we are going to be deriving the continuity equation from conservation of mass. I want to remind you that we are using these videos so you can closely follow along with the derivation. We expect that you will take the appropriate amount of time to understand each step. Additionally, we are going to be doing some math in this video, which includes partial derivatives. If you need a partial derivative refresher, the link to the Khan Academy video is posted above. Okay, so imagine we have an infinitesimally small cube in fluid with an arbitrary volume. Let the dimensions of the cube be expressed as delta x, delta y, and delta z, so that the area and the volume can be expressed as such. Fluid is flowing through this cube so that we have components of velocity in all directions. In this video, we're deriving the continuity equation from conservation of mass, but it's important to note that we can use any conservative tracer in place of mass. So the conservation of mass equation, in words, basically states that the rate of mass entering the volume, which is the same as the mass flow in minus the mass flow out, must be equal to the rate of change of mass inside the volume. Let's call this equation 1, because we'll come back to this equation a few times. We'll begin our derivation by looking at the left-hand side of the conservation of mass equation, and for now, we'll focus on flow in the x direction. Again, here's our cube, and now we can draw our x direction flow. We'll label the mass flow in each direction m in and m out. To determine m in, we need to know how much mass is coming through the yz plane of the cube. So we can define our m in as the density times the volumetric flow rate. This is equivalent to density times the flow velocity times the area that the velocity is flowing through, the yz plane in this case. M out is a bit more difficult to define. We start with the same flow that we had coming into the cube. But within the cube, there was some small change in mass. So when the fluid leaves, we have that very small change in flow rate leaving over the same area. We define this as the change in flow rate over the change in the x direction, multiplied by the length over which the change is happening, or delta x. This gives us our final equation for mass flow out. Together, mass flow in minus mass flow out gives us the rate of mass entering the volume, which is the left-hand side of the conservation of mass equation, or equation 1. We can simplify this equation down to one term by distributing the negative sign, and our final equation for flow in the x direction is given by equation 2.1. Now we'll look at flow in the y direction. The same logic as before applies, except this time our velocity is flowing in the y direction, so our component of velocity is v, and the area it is flowing through is delta x times delta z. Our final equation for flow in the y direction is given by equation 2.2. Finally, we have flow in the z direction with a velocity component of w, and the area is flowing through is delta x times delta y. Our final equation for flow in the z direction is given by equation 2.3. The net mass flow rate into the volume is simply the sum of these three equations, 2.1, 2.2, and 2.3. This gives us the final equation for the left-hand side of the conservation of mass equation. We'll call this equation 3. The net mass flow must be accompanied by a corresponding increase or decrease of fluid mass within the volume. So we'll now focus on the right-hand side of the conservation of mass equation, which can be described by the change in the density times the volume of the cube in time. We know the volume of our cube isn't changing, so we can simply remove it from the partial derivative, and our final equation for the right-hand side of conservation of mass equation is given by equation 4. We now plug equation 3 into the left-hand side of the conservation of mass equation, and equation 4 into the right-hand side. The volume appears on both sides of the equation and can simply be dropped. And after some rearranging, our final equation is called the continuity equation. This is the form that we will most commonly use for the continuity equation. However, you may sometimes see it written in vector notation. Vector notation uses the gradient operator to simplify the partial derivatives and velocity component in each direction. Using vector notation and the gradient operator, we arrive at our final continuity equation in vector notation. There are a couple of common simplifications we can make to the continuity equation. First, we expand using the chain rule. In a steady flow, or a flow in which the velocity at a fixed point is not changing with time, the density won't change with respect to time, and we can drop the first term. If the fluid is incompressible, the density is constant within a fluid parcel, so the density will not change as a function of x, y, or z, and the density will not change as a function of time. We can drop the first and the second terms, and we are simply left with one final term. In most cases, we make the assumption that the ocean is incompressible, so you will often see the simplification of the continuity equation.